Math. Okay. So some of this thing we're going to start with here is a little bit of a review of what we did last week, but just a reminder. If a quadratic, which is the equations we were working with last time, f of x equals ax squared plus bx plus c, has two imaginary zeros or two irrational zeros, they come in what we call conjugate pairs. And those conjugate pairs, if you don't remember, that happens because you might remember the quadratic formula has that plus minus in it. So that's why when we get imaginary answers or irrational answers, they look very similar to each other, except one has a plus and the other one has a minus. So when you're finding zeros, if your first zero happens to be something like 2 plus the square root of 3, your other zero would be 2 minus the square root of 3. That's called a conjugate pair. And that's how they come when they have the square root in them. That also works when they have the imaginary in them, or the I in them. 4 plus 3i, 4 minus 3i. Or even nastier, negative 6 minus the square root of 2i, negative 6 plus the square root of 2i. Because these imaginary zeros and the irrational zeros keep that plus minus in them, then you get these conjugate pairs for your zeros. It's pretty cool to know that you can kind of predict what one zero is when you know the other one. So the vocab for this, just so we're all clear, because I know the vocab can get kind of dicey, often we just use the word conjugate for real numbers. So the mathematical statement that you might make is this. 2 plus 3 times the square root of 5 has a conjugate of 2 minus 3 times the square root of 5. That's how you use the word conjugate. 2 plus 3 times the square root of 5 has a conjugate of 2 minus 3 square root of 5. With imaginary numbers, we use the term complex conjugate. You'll hear both complex and the word conjugate. So you'd say something like this. 2 plus 3i has complex conjugate 2 minus 3i. And it's not like the one with the plus in it is more important than the one with the minus in it, so it actually works either way. Someone could just as easily say 2 minus 3i has complex conjugate 2 plus 3i. It's not like one of them is the most important and the other one's the complex conjugate. They're complex conjugates of each other. So you don't need to say this one comes first and this one comes second. They just go together. There is a notation that people sometimes use for complex conjugates. If you ever see something like this, z equals 2 plus 3i, and then the question is z, the line over it, equals what? And everyone, you read that aloud as z bar. That's how you read that out loud. If you ever see a question like this, that's the mathematical notation that's asking for the conjugate. So if they say z equals 2 plus 3i, and they say, what is z bar equal to? And you say that's 2 minus 3i, and you win. So there's kind of really two cool things about these complex conjugates, the one with the imaginary numbers in them. The first cool thing is that they come together as zeros. So when you're finding the zeros of a quadratic, and they're imaginary, there'll be these complex conjugates, there'll be these pairs. The other thing that's cool is if you multiply a complex number by its complex conjugate, you get a real number. I'll write that down. If you multiply complex conjugates, the result is a real number. What do I mean by that? Well, the complex conjugate of 4 plus 5i would be 4 minus 5i. And according to what I just said, if I multiply those two numbers together, I'm supposed to get a real result. Not zero. I'm not talking about zeros right now. I'm just talking about getting a real number. So if I FOIL or smiley face this thing, then I'll get 4 times 4 plus 4 times 5i plus 4 times negative 5i minus 5i times 5i. So I'm not promised anything except this is supposed to be a real number when I'm done. Well, that's going to be 16. These are going to cancel because one's positive, one's negative. And this is going to be minus 25i squared. Well, I didn't get rid of the i's at all. What gives? Well, wait. What's I squared equal to? Negative 1. Oh. So I did get a real number. Oh, okay. So that's the other cool thing about complex conjugates. The first cool thing is that if one of them's a 0, then the other one is also a 0. And the other cool thing is if you multiply them together, you get a real number. All right, cool. Complex conjugates. Got it. Question?
Can we skip like the foiling method?
Okay. So let's talk a little bit more about these imaginary numbers. And some of this will be a recap from last time, some of it's kind of new. But imaginary numbers do not show up on the number line, which we did mention last time. They also do not give ordered pairs on a graph. That's interesting, everyone, because normally what happens is if we plug an x value into a function and it spits out a y value at us, that's how we find an ordered pair, a point we can actually plot on a coordinate system. But imaginary numbers, because they're imaginary and don't show up on the number line, do not give us ordered pairs. You see, square root of negative 3 is not on the number line. This number line is full of positive numbers, negative numbers, 0, rational numbers, irrational numbers, long decimals, big fractions, but you're not going to find imaginary numbers anywhere on there. And if an imaginary number doesn't belong on here anywhere, then when you plug it into a function and get a result, you can't have an ordered pair because the x value doesn't show up anywhere on the number line. So if I have a function, and here's a function we know pretty well, I can plug numbers in here all day long and get ordered pairs. I can plug a 3 in there, and I can get a 9. 3 squared is 9. I can plug a negative 2 in there, and I can get a 4. Now if I plug an I in there, everyone, I'm going to get I squared. And what is I squared? Negative 1. And 3, 9 is an ordered pair. Negative 2, 4 is an ordered pair. But I, negative 1, is not an ordered pair. There's no way to plot that because it has an I in it. So, imaginary numbers do not give ordered pairs. You're not going to see people writing like this in this class. More advanced classes, people do find a way to graph imaginary numbers, but you can't do it in the regular coordinate system that we use. So we don't do it. Well, let's keep building. Let's keep building up. We are building towards something. So let's take a function like f of x equals x squared minus 4. Now we know this function. Whether or not you're super comfortable with it, hopefully with a little reminder, you will agree that that's just going to be the x squared graph shifted down 4 units. because we did some transformations in our previous unit. If someone told me to find the zeros of this, I don't need the quadratic formula for this one. I just take the equation, oops. I just take the equation, set it equal to 0, move the 4 over, apply the square root property, and I get plus or minus 2. Those are the zeros. The zeros are 2 and negative 2. And they're real numbers. 2 and negative 2 are real numbers. And if your zeros are real, and I'll write this down. If your zeros are real, they correspond to x-intercepts on the graph. If you find the zeros of an equation, and your zeros that you find are real numbers, then you didn't only just find 2 zeros, you found x-intercepts on the graph, because I can take those zeros, and if I plug either one of those zeros into the original function, I of course get an answer of 0, because that's what a 0 is. But those directly correspond to 2 ordered pairs on the graph itself. In other words, x squared minus 4, which is our x squared graph shifted down 4 units, has a point here and a point here. The zeros correspond to x-intercepts. It has a point here, because the point that was at 0, 0 shifted down 4 units. Down here to 0, negative 4. That, everyone, by the way, is the vertex. And the graph looks like that. So, a real 0 gives an x-intercept of a graph. But it has to be a real number, because imaginary numbers don't become ordered pairs and therefore don't correspond to x-intercepts. Let's look at another function that doesn't look much more complicated than the one we just did. X squared plus 4. And this is just our x squared graph shifted up 4 units. Well, what would this graph look like? Well, it's not an award-winning picture, but does everyone agree that that's roughly what the graph looks like? Okay, now, look carefully at that graph I just drew. Does that graph ever hit the x-axis? X-axis right down here. Does this graph ever touch the x-axis? No. No x-intercepts. And here's what goes on, everyone. If someone told me to find the zeros, I would set it equal to 0, subtract the 4 from both sides, and apply the square root property. After last class, are we okay taking the square root of a negative when we're solving for x? Does that happen sometimes? Yeah. We all know the square root of 4 is 2. So what's the square root of negative 4 going to be? 2i. It's going to pick up an I. Yeah, this is going to be plus or minus 2i. So our zeros are 2i, negative 2i. And there's nothing wrong with saying those are zeros. You should say those are the zeros. But imaginary zeros do not show up on the graph and do not correspond to x-intercepts and are not ordered pairs. So if you get imaginary zeros, that's great. Maybe you did the problem perfectly. But do not try to turn them into ordered pairs. Do not try to find them on the graph. And do not call them x-intercepts. They are not. So if someone wrote this, no. Yes, they plug into the function to give you 0, but we do not express that as an ordered pair. You could write this. This is fine. What was my function? G of x? Yeah, you could write this. That's okay, but don't write it as an ordered pair. So, let's say someone says, I'm thinking of a function, f of x, and it has two zeros. And the zeros are -3 and 4. Those are the zeros. Are those also going to correspond to x-intercepts, if they're the zeros?
Yeah.
Yeah, because what kind of numbers are they?
Real.
They're real numbers. So they're also x-intercepts. And you can write them as ordered pairs. That's great. That's what you should do. You should understand that a real zero is basically the same thing as an x-intercept. Slightly different notation, but they're directly connected to each other. If someone else says they have zeros, 3i and -3i, is it possible that those are the zeros? Could those be the zeros? Absolutely, those could be the zeros. Yes. But then if they start to go like this and say the x-intercepts therefore are 3i, should you stop this person? Yeah, you should stop this person. They can't do that. They can't say those are the x-intercepts because those are not going to show up on the graph. In fact, we can even say this. If the only zeros of a function are imaginary, then the graph never touches the x-axis. If the only zeros of a function are imaginary, then the graph will never touch the x-axis. And that is not as profound as you might think. In fact, we already saw an example of that. This right here. That's a perfectly innocent looking function. It has a perfectly innocent looking graph. A graph, this has been shifted up 4 units, no problem. But it never touches the x-axis because its two zeros are imaginary. So that's nothing sinister or anything like that. It just means some graphs don't touch the x-axis, and if they don't touch the x-axis, then they probably have imaginary zeros. Okay. So, seem to be spending a lot of time on quadratics, and I'm doing that on purpose. That's actually a pretty big part of this unit, is quadratics. And quadratics, if you remember from last time, look like this. Quadratic could have 3 terms, an ax squared plus bx plus c. It needs to have that x squared term. The other 2 are optional. You see, something as simple as this is a quadratic. In fact, you might even remember back when we first learned our 5 basic functions, I called this the basic quadratic. If you don't remember, that's okay. But they can also look like this. -17x squared plus 687x minus 12.2. is also a quadratic. Obviously, that one's a lot more complicated, but they're both considered quadratics. You see, all quadratics and all lines except vertical lines. I don't hate vertical lines, they're just not functions, so they don't fall in this category I'm about to talk about. All quadratics and all lines except vertical lines belong to a large family of functions called polynomials. Polynomials are a big part of this unit also, this second unit in chapter 3. All quadratics and all lines except for vertical lines, so we're not talking about vertical lines, belong to a large family of functions called polynomials. Some people think that polynomials are kind of grim because there's a lot to remember, but it turns out that polynomials are very well-behaved functions. And I'll tell you what I mean by well-behaved, because that might sound kind of bizarre. You see, all polynomials, which I'll tell you more about in just a moment, all polynomials have domain negative infinity to infinity, which means yes, of course, you can plug in any x and it goes left and right forever. That's kind of nice. When you're dealing with a polynomial, you don't need to worry about domain, everyone. You don't even need to worry about domain because they all have domain negative infinity to infinity. Plug in anything you want. And, except for lines, which of course are straight, they are smooth curves. They don't have any sharp corners in them. They don't have any holes or gaps in them. They're just nice, smooth curves. They're very nice functions. What's not so nice is if someone asks you what a polynomial is and you look up the definition in the book, because this can give anyone a headache. Hey, what's a polynomial? Well, I'll tell you what a polynomial is. It's quite simply a polynomial function of degree n, and the variable x is a function defined by p of x equals a sub n x to the nth power plus a sub n minus 1 x to the n minus 1 power plus ellipsis plus a sub 1 x plus a sub 0, where each a sub I is a real, a sub n doesn't equal 0, and n is a whole number. Of course that's what a polynomial is. And since that's clear to us, we'll move on. No, that's annoying. So let's talk about what that means, everyone. To be a polynomial, all powers on your x's need to be positive integers. 1, 2, 3, 4, dot, dot, dot. If you have a power on an x, it can't be a fraction, it can't be a decimal, it can't be a negative. It has to be a nice positive integer. You may also have a constant. A number with no x, just hanging out at the end. We saw that with quadratics. Sometimes they had a plus 7 at the end or a minus 12 at the end. So, all your x's need to have integer powers that are positive numbers, not fractions, not decimals, not negatives, and you're also allowed just to have a number hanging out at the end. So far, so good. Other one's a little bit trickier. The other condition is this. All the coefficients, which is just a fancy way of saying the numbers in front of the x's, all the numbers in front of the x's, and your constant at the end, must be real, meaning you don't have any i's or square roots or negatives. There won't be anywhere in the initial equation. You won't see an I anywhere. And in Math 121, the college algebra class you're in right now, we're going to keep our polynomial simpler by saying all the coefficients must be rational. So you're not going to see any square roots anywhere in your polynomial either. So you're not going to see any square roots, you're not going to see any i's. But it is important to note that even though the powers on the x's are going to be nice numbers like 1, 2, 3, 4, 5, 6, 7, nice clean positive integers, the coefficients, the numbers that are in front of the x's, can be fractions, decimals, or negatives. So you might see fractions, decimals, or negatives in a polynomial. You're just not going to see them in the powers. And that's basically what that rule up there is trying to say. That's basically what this definition here that's a big mess is trying to say. That all your powers need to be nice positive integers, and all your coefficients need to be rationals. So let's look at an example. Let's look at an example of what a polynomial is. And they're good equations, everyone. There's a lot of things we can predict about polynomials. But this is a polynomial. Look at the powers on x's. There's a 7, there's a 3, and a 2, and there's a visible 1 on the x at the end there. There's also a constant. Yes, there's some negative numbers in here, but the negatives are on the coefficients, not on the powers. In fact, polynomials are so well behaved, one of the things you can say about a polynomial is you can say its degree. And what's the degree? The degree is just the highest power you see. So what's the degree of that polynomial?
7.
7. It's a degree 7 polynomial. It's the highest power. Is that okay that there's an 18.3 there at the end? Yeah, because that's not one of the powers, that's just one of the coefficients of the constant in this case. Those are allowed to be decimals. What is the degree of this polynomial? Degree 2. In fact, a degree 2 polynomial has a special name. Anyone know what the special name of a degree 2 polynomial is? It's called a quadratic. Ax squared plus bx plus c. That's what a quadratic is. It's a second degree or degree 2 polynomial. Huh. I love polynomials. I could write polynomials all day. 5x to the 4th minus 7x to the 3rd plus 2x to the negative 2 plus 9. What do you think, everyone? Wait, is that a polynomial? Look at those powers. Is a polynomial allowed to have a negative power? No. No, it's not. So remember your rules for polynomials. Those powers need to be positive integers. It wouldn't even make sense to tell someone the degree of this because it doesn't have a degree because it's not a polynomial. So you wouldn't say degree 4, but it's not a polynomial. You just say not a polynomial. Which doesn't mean it's not worth our time. It just means it's not what we're talking about right now. Okay, so that's what a quadratic is. We learned about quadratics last time. Quadratic is a type of polynomial. It just happens to be a polynomial where the highest power is 2. A quadratic is the exact same thing as a degree 2 polynomial. We're going to spend some more time with quadratics. Because sections 1.4 and 3.1 are about quadratics, these second degree polynomials, or these degree 2 polynomials. And that doesn't mean other polynomials aren't important, it just means that's what we're going to focus on right now, is the degree 2 polynomials. A quadratic is the name of the equation. When you see the equation, ax squared plus bx, darn it. When you see the equation, ax squared plus bx plus c, that's called a quadratic. The graph, and I've used this term before, but see if you remember, the graph is called a what? What do you call the graph of a quadratic? Anyone remember? It starts with P.
Parabola.
Yeah, it's called a parabola. It almost looks like you can pronounce it parabola, but it's parabola. And what is a parabola? Well, a parabola looks like this. Or a parabola might look like this. These are both parabolas, and every quadratic has a graph that's called a parabola. And I'll tell you something about parabolas, everyone. They're always symmetric, but not always about the y-axis. Remember when we talked about symmetry, we talked about even functions that were symmetric over the y-axis? Well, these things are always symmetric, it just might not be over the y-axis. You see, this one is symmetric over this line right here. It's the same on both sides of that dashed line I just drew. So they are symmetric, they're just not considered even functions all the time. So what my job is for the next part of this lecture is to teach you all about these quadratics. So I'm going to start with an example that I'm going to go through super fast. And you're going to be like, are you trying to teach us right now, or are you just showing off? This first example, I'm just going to kind of show you what we're building towards. So I'm not going to explain it super well as I go through it, because that's what the rest of the lecture is for. Check it out. This is what we're building up to, everyone. And some of this stuff you already know how to do, some of it you might not. But we're building up to this. F of x equals x squared minus 2x minus 3. Now we already know how to find the zeros of this. And the fastest way to find zeros, if it's possible to do it, is not the quadratic formula. What's the fastest way if it's possible to do it?
Equal to 0.
Factoring here, yeah. Breaking it up and factoring it. X minus 3, x plus 1. And even the fastest factorer in the world can still mess up this last part where you actually find the zeros. And once we find the zeros and we identify them as real numbers, and are these real numbers, 3 and negative 1, are those both real numbers? What else are the zeros also? What else can we call them? If we turn them into ordered pairs, what are they? They're the x-intercepts. Very good. But what we're going to do, everyone, is, let me get a graph in here for myself. Is I am going to teach you how to look at the equation of a quadratic like this. And the thing we already know how to do is find the x-intercepts. Right here and right there. There's an x-intercept, and there's an x-intercept. But I'm going to show you how to find the vertex. The vertex for this one happens to be right down here. The vertex is the center where it all comes together. I'm going to show you how to find the vertex. I am going to show you how to find this dotted line, which is called the axis of symmetry. It is the line that this parabola is symmetric over. I'm going to teach you how to look at an equation of a quadratic and generate this graph. And with confidence, we're going to give the domain, because it's always the same. And I'm going to teach you how to find the range and everything. We're going to learn all about this. We're going to learn about this point right here, the y-intercept. We'll learn everything we possibly want to know about one of these, because I want to get you to a point where you can look at this equation and say, there's a quadratic or a degree 2 polynomial, and you can say its graph is a parabola. And you're going to be able to just shred it. It comes with every piece of information you can about it. You're going to learn how to do that. This right here was not me teaching it. This was me telling you what I'm going to teach you. By the way, everyone, this one we can cover right now. Y-intercept is actually one of our favorite things to find. Plug in 0 for x and get the y value. It's almost a free ordered pair, because usually it's not so bad to plug in 0 to a function. Look at this, everyone. If I plug 0 into this thing, what's the only thing that doesn't cancel away? The negative 3. That's how we know that the y-intercept is 0, negative 3. So once again, let me reiterate, and I know I've said it a couple times already. You are not supposed to follow everything I did here. I did it fast on purpose to show you where we're going today. So just keep that in the back of your head what I'm building up towards, and you'll do just fine today. All right. Let's start chipping away at these quadratics and the graphs that go with them. They're parabolas. Let's see what we can find out. In Math 121, all our parabolas, I don't need an apostrophe on that, all our parabolas are functions. It is possible when you're studying other things in math, that you will study parabolas that open up to the left and right instead, like this. And those can still be called parabolas. The reason we don't focus on those in this class is because those aren't functions. They fail the vertical line test. So while these are parabolas, we're not going to see them in this class, so you don't need to worry about those. But if you're talking to someone who's taking another math class and they're saying we're doing parabolas that open left and right, then you can know that those exist. We're just not going to cover them. So in our class, all parabolas open up or down. They all do. And once again, all have domain negative infinity to infinity. So every parabola that we draw will either open up like that or down like that. They'll all have a point right in the middle, which we call the vertex of the parabola, arguably the most important point. They all have an imaginary dashed line going right down through the vertex, which we call the axis of symmetry. It might not seem like a big deal now. The axis of symmetry is actually pretty helpful. All of them have domain negative infinity to infinity. They all go left forever, and they all go right forever, and more importantly, what that means is you can plug in any x value you want and get a y value. However, the vertex will either be the highest point, so you might have a vertex that's the highest point, or the lowest point. Oops, now that makes sense. Or the lowest point. So even though the domain is negative infinity to infinity, do you think this thing goes both up and down forever? No, it bottoms out or it peaks out. It's going to be one of those two things. It either has to have a highest point or a lowest point. So all we'll say about that right now is the range is never negative infinity to infinity. Whenever you draw a parabola, everyone, every parabola has a vertex. Every parabola has a vertex on it. And the vertex is either the lowest point or the highest point. So a parabola cannot go both up and down forever. It has to stop somewhere. Yes, this one right here that opens up goes up forever. This one that opens down goes down forever. They don't do both. So the first thing we want to determine whenever we're faced with a new quadratic, a new equation, is to say, if we were to draw the parabola that goes with it, how does it open? And you might actually already know this. A quadratic's going to look like this. That's the equation. And if the number in front of x squared is positive, it opens up. And if the number in front of x squared is negative, it opens down. If that sounds familiar to you, it turns out that is directly related to a reflection over the x-axis. I'm not going to quiz you on this right now. I'm just going to ask a simple question. When we learned about transformations, did we do reflections? Did we sometimes flip a graph over? Yeah, the way we did that was with a minus sign. So making this a, this number in front either positive or negative, will tell you if your parabola is going to open up or down. What else do we know? Well, the graph's a parabola. Every parabola hits the x-axis once, twice, or not at all. Every time you draw a parabola, one of three things is going to happen. It's either going to touch the x-axis twice, it's going to touch it once, or it's not going to touch it at all. What do you mean, Steve? Well, here's what I mean. In general, using the quadratic formula or factoring, do we know how to find the zeros of a quadratic? Can we find zeros? All right, there's several different options for what can happen when you find zeros. You could find that you have two real zeros. And if your zeros are real, then you have two x-intercepts, which means you will cross the x-axis twice. Meaning, if you have two x-intercepts, your graph is either going to hit the x-axis twice and go up, or it's going to hit the x-axis twice and go down. But you're definitely going to have two x-intercepts if you have two real zeros. That's directly related to this. B squared minus 4ac is greater than 0. Once again, I'm not quizzing you. You don't need to take out a piece of paper and put away your notes. But that's the discriminant from last time. That was the thing that was inside the square root of the quadratic formula. It told us what kind of zeros we had, if they were real or imaginary. If you have two imaginary zeros, then you have no x-intercepts. Graph is always above or always below the x-axis. It doesn't mean the graph doesn't exist. The graph still exists. But if your zeros are imaginary, then your parabola might look something like this. Or it might look something like this. It just never gets to touch the x-axis. It has no x-intercepts. That's okay. We saw one earlier, x squared plus 4, never touch the x-axis. That's what happens if you have two imaginary zeros. It means you ended up with a negative under the square root when you were finding the zeros with the quadratic formula. So they might touch it twice. They might touch it none at all. Was there a third option? Yeah. You might have one real zero, meaning you have one x-intercept, which means vertex is the x-intercept. It is on the x-axis. If you have one real zero, just one, then that real zero, that place, is your one x-intercept, and it also happens to be your vertex. So that would look something like this, where your vertex is right on the x-axis, and it's also your zero, it's also your x-intercept. That happens when you use the quadratic formula. You get a 0 under the square root. That's a lot of information, I know. That's why I write it down for you, and that's why I record my lectures. So every parabola you draw, ever, is going to hit the x-axis twice, once, or not at all. And these are the conditions that happens. Either you have two x-intercepts where you cross, you have no x-intercepts, so your parabola is either above or below the x-axis but never touches it, or maybe you have the case where your vertex is right on the x-axis and you only hit the x-axis once. You can plug 0 into any quadratic and get one y value, which means every parabola has exactly one y-intercept. Any parabola you draw will hit the y-axis once and only once. Only once do you get to hit the y-axis. If you had two y-intercepts, then you wouldn't have a function. So that's not going to happen. If you had no y-intercepts, that would mean 0 is not in the domain, and 0 is definitely in the domain. So neither of those things is going to happen. You always have one y-intercept. How many x-intercepts do you have? Maybe one, maybe two, maybe none. So it turns out you can actually tell quite a bit just from what we've covered so far. Check this out. Here's a parabola, everyone. I don't know what the equation is that goes with it, but it looks something like this because this is a quadratic. What can you tell me about the equation, though? Can you tell me anything about it just by looking at the graph? Well, you can tell me that A is either positive or negative. Is A positive or negative? Positive. A is greater than 0 because the graph opens up. You can also tell me that because the graph has two x-intercepts, that means that it has two real zeros. You can also actually say that C is negative because of the y-intercept. The y-intercept is down here, so C must be a negative number. You can actually tell a lot by looking at a graph. Look at this one right here. Do we know if A is positive or negative?
Negative.
Yeah, it's got to be negative. It opens down. A less than 0 because this thing opens down. Let's see here. No x-intercepts. Does no x-intercept means it has no zeros, or what does it mean? If there's no x-intercepts, what does that mean? Brilliant. Two imaginary zeros. Very good. And once again, C is less than 0, because even though I can't see the y-intercept on here, I can see that it would be down here. And finally, look at this one. Well, A is greater than 0 because it opens up. How many x-intercepts does this one have? One x-intercept, meaning this one just has one real 0. And C is going to be positive. By the way, what about this x-intercept? Can you tell me anything else about the x-intercept, the one x-intercept? The x-intercept is also the vertex.
Wouldn't it also be the line of symmetry?
Yes, it does, and we'll learn more about that after our break today, but absolutely, yeah, that also tells us where our axis of symmetry is, absolutely. So, I'm going to teach you how to do everything with these quadratics, but no matter how much we do, it's going to stick around that the hardest thing is finding the x-intercepts, or finding the zeros. That's the trickiest thing. So what we're going to do after the break, everyone, and you will want the break, so make sure you get out of here. After the break, we're going to learn how to complete the square, which I think is awesome. When you're trying to find zeros, the biggest drawback to factoring is that you can't always factor. The biggest drawback to the quadratic formula is that it can be the biggest pain in the neck in the world to simplify. So my favorite technique for finding zeros is actually this technique called completing the square. Now, because I wanted the answer to work out nicely for our first example, this is a particular quadratic that you could factor. But we're going to find the zeros without factoring it. So what I've done is I've actually prepared some steps that I'm going to paste up here as we go. And this first example is going to take a long time because I'm going to explain everything as we're doing it. But then as we get further and further along, we'll see that they actually don't take this long. The first thing you want to do is you want to set your quadratic equal to 0 and move the constant to the other side using either addition or subtraction. So to start this problem, to find the zeros, I set the equation equal to 0. Then I will add, in this case, a 48 to both sides. That gets me started. You do not want to apply the square root property here. That's going to be a dead end. You want to wait, and we'll apply the square root property later, but it does not happen yet. Okay, next step. Like I said, there's a lot of steps here, but of course, I'll post this after class so you can look through it at your leisure. The next step is, in order to use this technique called completing the square, we can only have a 1 in front of the x squared. There cannot be another coefficient in front of the x squared. In this case, there's a 3. So what we need to do is we need to divide every term by the number in front of the x squared. You can actually do this as your first step or your second step. The first two steps are interchangeable. But either way, we do need to go through and divide every single term by 3 That way, instead of having 3x squared, we'll just have x squared. And we end up with x squared minus 6x equals 16. Okay, the third step is actually kind of the meat of this whole process. So, copy. And I wouldn't try to write down all these rules. I'll post them for you after class so you can have them. Here's the big step. You identify the number that's in front of the x, not the number in front of the x squared, which at this point should be a 1, but the number in front of the x, along with its negative sign if it has one. Then you do a little side work. So everyone, what's the number that's in front of the x? Negative 6. You take that number and you divide it by 2. You cut it in half, making it a negative 3. Then you square that result, in this case a 9, and you add that to both sides of the equation. So instead of just having x squared minus 6x, we'll have x squared minus 6x plus 9. And on the other side, instead of just having 16, we'll have 16 plus 9. So you take the number in front of the x, cut it in half, square it, and add it to both sides of the equation. Then you can simplify this side over here if you want to. So it's going to be x squared minus 6x plus 9 equals 25. Okay, now here's the cool part, everyone, and this is actually why the process is called completing the square. The side that has the x's can now be factored as a perfect square with 2 matching factors. In other words, this side, x squared minus 6x plus 9, can be factored where both factors are exactly the same as each other. Does anyone know what those 2 factors are?
Negative 3.
X minus 3 and x minus 3. Now some of you might be thinking, Steve, if I'm going to have to factor anyway, what's the point of this technique? Why wouldn't I just factor? Well, here's the cool thing, everyone. There's actually a way to know what this answer is right here. It was x minus 3, x minus 3. Does anyone see a minus 3 anywhere else on this board? Oh, look at this. Look at this, everyone. I'm going to use my creative pen. That number that we got when we cut the negative 6 in half is the secret to the factoring. This is what tells us that both of our factors are x minus 3. In fact, most of the time what you would do is you would just write it once. What is this thing? Get out of here. You would just write it once with a squared on it. That's why it's called completing the square, because now you have a perfect square over here. And once you have that perfect square over there, everyone, it is time to apply the square root property. Apply the square root property. The square root on both sides, include a plus minus on the number side. The side with the x's should have the square root and the square cancel each other out. So you put a square root over both sides, and this just ends up being x minus 3 equals plus or minus, in this case, what's the square root of 25, everyone? 5. Ta-da! Now, last step. Solve for x by adding or subtracting the number with the x to or from both sides. You'll have your zeros. If the zeros are imaginary or irrational, which they're not in this case, they will come in pairs, conjugate pairs. Either way, though, what we have, everyone, is x minus 3 equals plus or minus 5 becomes 3 plus or minus 5, because I add the 3 to both sides. Don't lose your plus minus that's on that number on the other side, because we still need that to get our 2 answers, because we actually have 2 answers here. We have x equals 3 plus 5 and x equals 3 minus 5. So we have x equals 8 and x equals negative 2. And those, everyone, are our zeros. Now, class, completing the square looks like an awful process, if you allow me just for theatrics to go like this. But most of that on there were the rules to how you complete the square. And these 6 steps are how I broke it up to do these problems. When you're doing these problems, you're not going to have to think to yourself, wait, what was the 4th step? What was the 5th step? You're going to find yourself just going through and doing the process when you practice enough. So those are not the universal 6 steps to complete the square. Those are Steve's 6 steps that he uses to explain it to a class. So, what do I need to tell you about completing the square? Well, it's a technique for finding zeros. If we were to take either of these numbers, 8 or -2, and plug them back into our original function, what would the result be? 0. That's what they are. They're zeros. So, completing the square is the reason we have the quadratic formula. You might remember our last class. Near the very end, I put up this huge mess that was solving ax squared plus bx plus c equals 0 into the quadratic formula, and it was a huge thing. It was terrible looking, but that was why we have this form. That's why we have the formula. What you'll be interested in knowing is this. You will be required to complete the square on an exam and show your work. We'll worry about that more later when we get close to the exam. I just wanted you all to take it seriously. You are going to have to learn this technique. That being said, there is a link on D2L to 5 YouTube video examples made by your teacher, Steve. You can probably find tons of people completing the square on YouTube, but there's 5 examples that I did that you can find. And there is an optional worksheet with answer key. And we're not done with this, everyone. I'm going to do a couple more for you, of course. That was just the first one. But I just want you to know that after today's class, when you're sitting there wondering, I wish I could see more of this because he told me it was going to be on the test, I wish there were more examples. There are more examples for you to look at, of course. All right, so at your leisure, everyone, and I realize I went way too fast for you to copy it all down. At your leisure, of course, go back and look at these steps so you know how to do this. But for now, let's try and do another one of these without writing down every little detail of what we're doing. We'll just show all our work. All right. Find the zeros by completing the square. All right. Now, you could write down the steps 1 through 6, but as I said before, the steps are almost going to kind of bleed into one another. And you're not going to, I think it'll be more trouble than it's worth trying to keep track of which step is which number rather than just remembering what you're supposed to do. In fact, I remember the first thing I'm supposed to do is get this thing and set it equal to 0, and then move the constant to the other side. But I also remember that I cannot complete the square when there's a 2 in front of the x squared. Does that sound like something I said in the previous example? So we got to divide everything by 2. And we're going to get fractions, but don't lose your cool, everyone. We can deal with fractions. I mean, if you have to deal with fractions, having a 2 is where it's at in the bottom. The process for actually completing the square, everyone, and this is the big step right here, is you take the number in front of the x off to the side. What's the number that's in front of the x, everyone? 7 halves. 7 over 2. Here's a tip for everyone. Cut a fraction in half by doubling the denominator. If you're concerned with how you divide a fraction in half, you just double the denominator. So half of 7 halves is 7 fourths. That's pretty slick. square a fraction, you have to square the top and the bottom. So if you're in a position where after you cut this in half, you have to square both the top and the bottom, you have to square it, you square both the top and the bottom. So this is going to be 49/16. Square it, don't double it, square it. This monstrosity, 49/16, is what we add to both sides. But I want to remind you, there was no guesswork involved. And unlike the quadratic formula, there's not a lot of nasty simplifying to do either. But I do need to add 49/16 to both sides. I can do that. Now, that right-hand side you're going to want to clean up a little bit. So let's put in a bubble of think right here. Here's our thinking bubble. If I want to add two fractions together, what do I need?
Common denominator.
Common denominator. What's my common denominator here, my lowest common denominator? 16. So if I just take this 1/2 and multiply the top and the bottom by 8, it will become 8/16. If I add that to 49/16, that's going to be 57/16. Does that sound okay to everyone? All right, so what do I have? I have x squared plus 7/2 x plus 49/16 equals 57/16. This looks like it's getting worse before it gets better. But I'm going to press on. Oh, shoot. I have to factor this side. How in the world do you factor that thing?
7/4.
What do you mean 7/4? How'd you do that so quickly? What's going on?
You gave us the answer.
Oh, shoot. I did give you the answer, didn't I? You win this round. Yes. It's not a guesswork factoring, it's a using your work factoring. When we cut this in half, we got 7/4. That's what goes right here. That's the secret to factoring. You do not need to guess. You do not need to stare at these fractions for 2 days saying, how in the world do you factor that? It's x plus 7/4. Now, we apply the square root property. On both sides, take a square root. This just ends up x plus 7/4. Well, I don't know the square root of 57, but do you know the square root of 16? 4. One step left. What's our last step going to be to get x by itself? Subtract 7/4. Now, if you used the quadratic formula, you could get this answer. The quadratic formula, though, is going to require a lot more simplifying, where you're kind of on your own to simplify, and you don't have these steps to follow. So I think this is actually easier, because it's a technique, not a formula. Are these real, by the way, these zeros? What makes them real? In other words, why are they not imaginary?
They are on the number line.
You got a positive number under the square root. There's no I, so they're not imaginary. Now, I don't really know what the decimal approximation for that is, but I do know those are real numbers. And if they're real numbers, even though you might not like me doing this, I am allowed to do this. Because as long as they're real, they do correspond to the two x-intercepts on the graph. If I were to graph this parabola, which I'm not going to do, but if I were to graph this parabola, it has exactly two x-intercepts. And where are they? Here and here. Completing the square does not have to be the most painful experience in the world. It does take practice, otherwise you're not going to remember all the steps. So before we leave it alone, and I tell you to watch the examples that I posted on YouTube, let's do another one together. So frustrating when suddenly you encounter a problem with different instructions than what you're used to, like this. But if you remember our class from last week, you might remember me saying, this is just another way of them asking us to find the zeros. Rather than saying find the zeros, they set it equal to 0 for us and say solve. But they might as well have just said, find the zeros, and given us a function. It's the same question. In fact, they've already done the first step for us. They set it equal to 0. So my first step is going to be to add that 11 to both sides. Someone else might say their first step is to divide everything by -9. It doesn't matter which one you do first because the first two steps that I showed you are interchangeable. You need to get the number to the other side, and you need to get nothing but a 1 in front of the x squared. So we will divide everything by -9. And here's another tip for everyone. And this is not the kind of tip that if you don't follow it, everything's going to go wrong. This is something I have found from my experience that helps me. Unless a fraction reduces to an integer, don't bother reducing till the end of the problem. You see, class, a lot of these problems you'll deal with fractions, and you're going to have to come up with a common denominator. So it turns out a lot of times if you reduce a fraction, you're just going to have to build it back up again later to get a common denominator. So when you're doing these problems, and this isn't the best example of that, but when you're doing these problems, I would not bother reducing a fraction unless you can reduce it down to an integer. 18 over -9 does reduce down to -2, that's fine. But if you have something else where you can divide both the top and the bottom by 2 and reduce it, I wouldn't bother doing it until the end, because you might just have to build it back up again anyway. What have I done so far? I moved the constant to the other side, I divided everything by -9, and now I'm ready to do the completing the square process. So what's the number I write off to the side? And it is -2. Now some people might say, Steve, if you're going to cut that in half, and then you're going to square it, why does it matter if it's a -2? Because if I'm going to square it anyway, I was going to get a 1 even if I just did a 2. And I would say you're right, actually. That's not going to hurt you on this step if you forget the negative sign. Where it will hurt you, though, is when you're trying to factor, because this is the secret to the factoring right here. And if you didn't bring the negative sign with you, then this number will be wrong. So make sure you bring that negative. Remember what we do. Divide by 2, square it, and then add it to both sides of the equation. Once again, I create my little brain work over here. -11/9 plus 1 is the same as -11/9. I love adding 1 because it's so easy to turn it into a fraction. You just write the number over itself. So 1 is the same as 9/9 or -2/9. The heck am I doing? Why am I doing? Oh, I'm doing this so I can factor the left-hand side. It's not guesswork. X minus 1, right there. It tells you exactly what you put next to the x. X minus 1. It's a beautiful thing, everyone. It tells you exactly how to factor every single time. No guesswork. Apply the square root property. You got it. Now I must be cautious. First of all, I hate that negative under there. Now I can get rid of the negative as easy as pie, just like that, as long as I put 1 on the outside. And I can also clean up that square root a bit. I don't know the square root of 2 off the top of my head, but do I know the square root of 9? Yeah, so I can turn that into a 3 on the bottom, outside the square root. One step away. Add the 1 to both sides. And I got 2 zeros, everyone. They are imaginary zeros, so they are complex conjugates of each other. 1 plus the square root of 2 over 3i, and 1 minus the square root of 2 over 3i. I'm in such a good mood, I think I'll write down the x-intercepts also. Doop-a-doop-a-doo, writing down the x-intercepts, because no one's trying to stop me. Writing down x-intercepts, this is what you do, because you have the zeros. Does anybody care? Should I be writing down x-intercepts right now? What do you mean, no? I'm the teacher, so I'm going to write down the x-intercepts.
They're imaginary.
What do you mean that? Oh. So when zeros are imaginary, they're not x-intercepts? All right. Fine. You all win. No x-intercepts. Now that doesn't mean that this graph is bogus. If we were to graph this thing right here, which we're not going to do right now, we'll graph some other ones later, that doesn't mean the graph doesn't exist. It just means the graph never ever touches the x-axis. Why? Because it had 2 zeros. The zeros were imaginary. That means no x-intercepts. So I was being a mathematical jerk right here when I was writing the x-intercepts. That's not okay. They're imaginary. I can't do that. What else do I know? If I were to graph that, do I know which way it opens?
Yeah.
How does it open?
Down.
Down, okay. Opens down, no x-intercepts. Graph is always below the x-axis. If you have a parabola that opens down and it has no x-intercepts, that doesn't mean the graph doesn't exist. That doesn't mean it's a faulty parabola. That doesn't mean it's not worth our time. It just means it never touches the x-axis. That's fine. It's always below the x-axis. Does everyone know that you can go on D2L and find links so they can watch more examples of these, complete the square? In fact, I won't even be standing in your way for those, so it's pretty cool. All right, so make sure you follow up if you watch more examples if you need to. And when Nina comes back, she'd be happy to help you with more examples of these too. I know she would. All right. So, let's take a break from that. What if I want to graph a parabola when given? Let's get back to that thing that I said I was building up to. Going from the equation of a quadratic to the graph. How do we get there? Well, let's talk about what we already know. Do we know how to figure out if our parabola opens up or down? It's actually pretty quick. A greater than 0, you open up. A less than 0, you open down. Pretty quick. What else do we know really quickly? Do we know the domain pretty easily?
Yeah.
Yeah, what's the domain of every quadratic? Yeah, I'll tell you, when I did the homework, I was getting livid. I was getting so tired of typing in it, because every time I worked with one of these, they said, what's the domain? And I was like, yeah, I get it. The domain of every quadratic is negative infinity to infinity. You'll get tired of it too, but it's good practice. Is the y-intercept that hard to find? The y-intercept. No, the way you always find a y-intercept is the same. You plug in 0 for x. In fact, when you plug 0 into a quadratic like this, everything dies except for the c at the end. That was those terms dying, everyone. And you get 0c. That's your y-intercept. Man, I can get a lot of information quickly. Now, the hardest thing usually to find is the x-intercepts. Fortunately for us, we have tools for finding those. You see, if the zeros are real, we can find x-intercepts by factoring, quadratic formula, or the thing we just learned, completing the square. So I'm not going to say finding x-intercepts is easy because it can actually be the trickiest part of the process, but I will say we have several different ways to find them. So I think we're in pretty good shape as far as finding x-intercepts. What is arguably the most important point on the parabola, though? The vertex. Let's talk about that. How do you find the vertex? Well, I'll tell you, the vertex is an ordered pair, everyone. And an ordered pair is an x value and a y value. And the way we typically find an ordered pair is we plug an x value into the function and we get a y value back out. So, here's what we need to do. We will find the x value of the vertex and plug it into the function to get the y value. Because if we can find the x value of the vertex, if we can find the number that we plug into the function, then finding the y value won't be that hard. You just got to run a number through the function, which we know how to do. So, how do we find the x value? Well, we have a couple ways. How do we find x value of the vertex? Well, there's a couple ways. One way you can do it is if you've already found your zeros, and it doesn't actually matter if they're real or imaginary. If you've already found your zeros, you can add them together and divide by 2. And that will actually tell you the x value of your vertex. So if you've already found your zeros, that's not a bad technique. You can rewrite the equation using a technique similar to completing the square. That's harder, and we don't know that one yet. That's something I'm going to tell you about next time, but we don't know that technique yet. So that's not really the best technique to rely on right now, but there is a way to rewrite the equation so you can tell where the vertex is. The one that most people use is this one right here. The x value of the vertex is found by doing negative b divided by 2a. That's the one that most people remember. The other ones work, but this is the one most people remember. It's the one most people prefer. You see, if someone gives me a quadratic and asks me to find the vertex is an ordered pair, but in order to find the ordered pair, I need the x value first. So, the way I find the vertex x value is negative b over 2a, or in this case, check it out, b is 12, so it's going to be negative 12 over 2 times 3. This will give me the x value of the vertex only. Negative 12 divided by 6 is negative 2. That's not your vertex. If I told you to graph negative 2 on a coordinate system, that'd be weird. We need an ordered pair. So, to find the y value, you plug the negative 2 into the function. In this case, you'll get negative 27. I'm not going to say that's the easiest thing in the world, but I will say it's something we can all do. Anytime you plug a number to a function, of course there's a chance you're going to make an arithmetic error, you're going to mess up a negative sign. That can happen to anyone. But that is how you do it. So if you were looking through your book later, and you're looking at vertex, you're going to see a formula probably that looks like this. Negative b over 2a to find the x value. And then f of negative b over 2a to imply that you find the y value by plugging the x value back into the function, which is exactly what we just learned how to do. What's the domain of every single parabola? Negative infinity to infinity. Is the range negative infinity to infinity? No, it's not, but I'll tell you something cool. if you know the vertex and the direction your parabola opens, you can give the range. If you know those two pieces of information, everyone, you can give the range. Check it out. Let's say I'm thinking of a parabola, and it has a vertex of -3, 5, and I also know it opens up, like that. I can give the range from that. Because every parabola either goes up forever or it goes down forever. What does this parabola do? Go up forever or down forever? Up forever. So the range of this parabola goes up to infinity. But the lowest point ever on the parabola is the vertex. So what's the lowest y value it gets to? 5. And it does get to it, so that's why it gets a bracket. See, as long as you know the vertex, you have the y value of the vertex, and you know which direction it opens, you can give the range. 7, 14. No one say anything out loud. Everyone write down what the range of this one is. Don't say it out loud. Write it down. Everyone's writing down the range. Everyone's first figuring out if they're going to be using infinity or negative infinity by looking at the picture. And then they're going to write down the other value. What does this one do? Down to negative infinity or up to infinity? Negative. Down to negative infinity and all the way up to what? 14 with a bracket. That's neat. Huh. That's pretty cool. I'm feeling pretty good about finding out all the information I need to know about a parabola. I wonder what else I can do. What else can I do? Every parabola has an axis of symmetry, which we show with a dashed vertical line. Now, class, little side note for everyone here. The homework may call the axis of symmetry just the axis. So if you're doing the homework problems, everyone, and they say, tell me about the axis, they're actually talking about the axis of symmetry. I saw that in a couple of homework problems. I don't know if they fixed that yet. So axis of symmetry and what the homework calls the axis are the same thing. Don't let that mess you up when you're doing your homework. Now, it's a vertical line through the vertex. And since it's a vertical line, is it going to be x equals or y equals if it's a vertical line? Vertical line? X equals. X equals for a vertical line, and it's going to go right through the vertex. So the x value is going to be negative b over 2a. In other words, x equals the x value of the vertex. So if you know the vertex, then you know the axis of symmetry. If you know that there's a parabola that has a vertex of -3, 6, then you know that this vertical line has an equation, x equals, because it's vertical, and what's the x value it's equal to? -3, exactly the same as the x value of the vertex. If your parabola opens down, like this, and it has a vertex of 78,642, what's the equation of the axis of symmetry? X equals 12. So you can find that axis of symmetry as long as you know the vertex. One of the things that's really cool about these parabolas is there's two things that everyone can figure out very, very quickly. Here is a rather nasty looking quadratic. And I am not interested in finding the x-intercepts of this. I'm not interested in finding the vertex right now. But there's two things I can find very quickly. One of the things I can find very quickly is I can figure out which way it opens. Does everyone agree with that? That's fast. Which way does this one open? Down, no problem. What's the other thing you can find out very quickly? The y-intercept. Because the y-intercept always starts with a 0, and in this case ends with what? Negative 12. Now, I'll tell you why this is convenient to know. Because granted, we still don't have the whole picture. We don't have the vertex here. We don't have the x-intercepts here. But here's what we do know. If we were given some sort of matching problem where they said match this equation with its graph, here's something you could do. Look at this. Let's say one of the graphs looks like this. Can we eliminate that one right off the bat? Yeah, it opens the wrong way. I don't know exactly what the graph looks like, but I know that can't be it. How about this one? Could that be the right one? Why can I do that?
Y-intercept.
The y-intercept. The y-intercept is right here. This one right here has a positive y-intercept. Where's my y-intercept? 0, negative 12. So could that possibly be the right graph? No. Now, I'm not going to tell you this is enough to tell you exactly what the graph looks like, but I will tell you if someone's trying to mess with your head and trick you into picking the wrong graph, you can get these two pieces of information so fast that you can immediately start eliminating bad answers right away. It's pretty slick. All right. Two more things for today. There are graphs that look like parabolas, but you may not call them parabolas unless the equation is a quadratic. The only function out there that will give a graph called a parabola is a quadratic. If it's not a quadratic, then the graph, no matter how much it looks like it, is not a parabola. Here's an example, everyone. F of x equals x to the fourth. This is a fourth degree polynomial, not a second degree polynomial, so it's not a quadratic. Its graph, if you were to do this like on a computer, actually kind of looks like a parabola with a flat tire. It's a little bit flatter on the bottom. It's very tempting to say, look at that parabola up there, but is this a parabola? Absolutely not. It's not a parabola because the graph, the equation that generated the graph is not a quadratic. Later in this class, and not actually that much later, in a couple weeks, we're going to see a function that will create a kind of nightmarish looking graph that might look something like this. That's right, everyone, you're going to be doing graphs like this before this class is over. Not this class, but Math 121. That little piece in the middle, does that look kind of like a parabola? Do you think it is a parabola? No, it came from a completely different type of function, so this is not a parabola. Now, if someone came in here and said, Steve, that looks kind of like a parabola, or that looks kind of like a parabola, I would say, yeah, you're right, it looks kind of like a parabola. But it's not a parabola because it didn't come from a quadratic. Question?
Is that like a piecewise function?
Actually, that's called a rational function. We'll learn about those in section 3.5. It's actually just one equation that generates that, but it's a nasty looking equation. But I'll teach you all about it. Last thing of the day. This is our cool down, everyone. Is that a quadratic, everyone? It sure is. What's the domain?
Negative infinity.
Negative infinity to infinity. Which way does it open? Up. What's the y-intercept as an ordered pair?
0, negative 5.
0, negative 5. You might need to think about it a little bit, but is it possible to give the range at this point? Yeah, what do you think? Does the range go up to infinity or down to negative infinity? Up to infinity. And what's the lowest y value it gets down to? Negative 5. Little trickier, but still possible. Do we know how to give the vertex of this thing? Yeah, what's that formula? Negative b over 2a. So it's going to be negative negative 4 over 2 times 1 or 2. Does that mean the vertex is 2? Or is it better to say that's half the vertex? Vertex is an ordered pair. How do I get the other half? Plug it in. I love it. Plug it in. How's that look? Does that look more like a vertex? Yeah, it sure does. Did I make a mistake?
Isn't the range different? Because it's not from the y-intercept? Isn't it from the vertex?
Yeah.
Well, good for you. Well, now I wish I wasn't even recording that. I got all excited about the end of the class. That's not the range, everyone. Say that again, what you said. How do we find the range?
From the vertex.
From the vertex, not the y-intercept. Well played. Good. Yeah, I messed up. I completely messed up. The range, we did have the right idea with the infinity, but I led us all astray. It should be negative 9. Well done. Well done. What's the last thing we might want to find? X-intercepts. X squared minus 4x minus 5. If it's possible to do it, what should we do?
Add 5.
We should factor it, but yes. Redemption for messing up the range. He cannot be stopped now, everyone. That'll be really cool if I got it right. Yeah, I did. Could you have factored this one also? Yes. Does completing the square always work? Always. So our x-intercepts, because those are both real numbers, are 5, 0, and negative 1, 0. Now class, give me a minute here, 1 minute, because I do have, it's only 2:48. With the exception of me botching the range here, which we fixed very nicely, look what we know how to do now. All those things I said we were going to build up to, we know how to do. And do you think, if we know a y-intercept, if we know the vertex, if we know the x-intercepts, and if we know the axis of symmetry, that's going to be enough for us to draw a pretty good graph of the parabola? Yes, and I would do that right now if we have time, but we don't. So when we come in next time, we're going to keep working with quadratics for a little while, and we'll graph a parabola. Because we know everything we can do. We can tear apart a quadratic, and we can draw the graph. Because we're awesome and because we're smart.